With numerical integration, solving for the area below a curve is not so excruciating anymore. Check an example here in numerical solutions to see problems. Before delving on the different methods, let's compare analytic and numerical integration in solving for areas. Say a function describes a curve and the area under is bounded by a and b. Exact integration utilizes integral strips with dimensions of y and d of x. The total area is then the integral of y dx or f of x dx from a to b to solve for the exact area. On the flip side, numerical integration then adopts the same concept of working with strips, but this time, the number of strips are provided instead of integrated. The area of each strip is solved and the summation is taken. The given function for this example is 3x squared plus e raised to x, with the limits from 0 to 3. The area will be approximated using 6 integral strips by the methods of midpoint rule, trapezoid rule, and Simpsons 1/3 rule. Before starting with any approach, identify the base parameters. Given the function, draw a Cartesian plane, and from the limits, it shows that the curve is measured from 0 to 3. So the total base length is 3 minus 0, giving 3. The instruction is to have 6 parts, which provides delta x as 3 divided by 6, or that is 0.5. Thus, the strips have x coordinates of 0.5, 1, 1.5, 2, and 2.5 in between the limits. With the midpoint rule, we take the midpoint of each strip, giving another set of x coordinates, which are 0.25, 0.75, 1.25, 1.75, 2.25, and 2.75. These are the coordinates we use to take y values using the function. Placing 0.25 into the function provides y as 1.4715. If x is taken as 0.75, the function yields 3.8045. At x of 1.25, y turns to be 8.1778. And if x is 1.75, y is solved as 14.9421. Moving further, when x is 2.25, y is 24.6752. And when x is 2.75, y results to 38.3301. To create a rectangle, each of these y values are multiplied by the base, which is 0.5. And to generate a bigger area, individual calculations are added together. So instead of doing the process separately, add all the y values and multiply everything by delta x, which is 0.5. The total area using midpoint rule is then computed as 45.7007 square units. The trapezoid approach does not need any midpoint after identifying the coordinates of the bases, so directly solve for the y values, where y is 1 when x is 0. At x of 0.5, y is taken as 2.3987. When x is 1, y turns out as 5.7183. At x of 1.5, y is computed as 11.2317. Also, When x is 2, y comes to be 19.3891. At 2.5, the function yields y as 30.9325. And when x is 3, y becomes 47.0855. These are the values used as bases in the trapezoid area, and cumulatively, we can write the summation of trapezoidal areas as a half of delta x, which is 0.5. Then take the first y as 1. Then add twice of 2.3987, also twice of 5.7183, and twice of 11.2317. There are also twice of 19.3891 and 30.9325. Then end the computation by adding 47.0855. The area under the curve is then simplified as 46.8565. When using the Simpsons 1/3 rule, the basics are practically similar with the trapezoid rule. Thus, the y values will be used as computed earlier. The only difference this time is the cumulative computation of the strip series. The area then starts with a third of delta x. Then this is multiplied by the first y, which is 1. Add to this 4 times of 2.3987, then twice of 5.7183. Follow this up with 4 times of 11.2317, then twice of 19.3891. Then again, 4 times of 30.9325, plus the last y value of 47.0855. The area using Simpsons 1/3 rule is then simplified as 46.0920. The different approaches yielded different areas, but then the differences are minimal. But again, the most accurate is that of Simpsons as 46.0920.